In section 2.2, we're going to look at separable equations. We begin our study of solution methods with the simplest of all differential equations. These are the first order equations that are separable in variables. If you've seen a differential equation before, perhaps maybe it was at the end of like a Calc 1 class or maybe even in Calculus 2, odds are it might have been one of the following types we're about to see. Okay. So the basic idea is that, if we're trying to solve especially a first order differential equation, we know that the inverse idea behind taking a derivative is taking an antiderivative. So sometimes if you're able to separate the variables, get all of the y terms on one side and all of the x terms on another side, then we can actually integrate both sides of the equation to find our solution. Okay. So for example, let's consider the first order differential equation dy dx equals f of x comma y when f does not depend upon the y variable. So this is kind of like the exact opposite of an autonomous differential equation. Instead of having y dependence only, let's suppose we have just x dependence. If that's the case, if dy dx is equal to some function of x, then we can simply solve this by integrating both sides. We take the integral of the left-hand side with respect to x, take the integral of the right-hand side with respect to x. The antiderivative and the derivative cancel, so we would get y equals the antiderivative of the right-hand side, which if we represent it using the classic notation capital G of x plus c, that would be our solution. For example, if we had dy dx equals to just some function of x, you would integrate both sides. The antiderivative of 1 plus e to the 2x. Antiderivative of 1 is x. Here you would want to do a u sub for the variable, but this antiderivative would be 1/2 e to the 2x, plus we have our constant of integration. If we have an initial value problem where they tell us the value of y at some initial point, then we'd be able to solve that initial value problem by evaluating it and solving for the constant of integration. So this is what we mean by separable variables. The f of xy doesn't necessarily have to be a function solely of x, by the way, in order to do this. But in general, if f of xy can be factored, if you can write it as the product of some function of x times some function of y, then we're able to go ahead and separate the variables. So a first order differential equation of the form dy dx equals some function of x times some function of y is said to be separable or to have separable variables. Okay. This one, for example, would be separable because you have it written as a product of stuff that involves x's and y's. If I wanted to be even a little bit more explicit with this first one, let me do that. So what you would see here is this term, we could rewrite this as e to the 3x times e to the 4y, and then it's possible to rewrite dy dx as follows. I have this x term, we have an e to the 3x, and then we have a y squared, and then we have the second term, which is the e to the 4y power. Here we've written dy dx as the product of some function in x and some function in y. So this differential equation, the first one, would be separable. Okay. However, the second one, this dy dx equals y plus sine x, is not separable. We have a collection of two terms that are added, and we cannot write that as a product, a multiplication of a function of x and a function of y. As we just said a moment ago, here you can kind of see that explicit writing of f of xy. We're able to rewrite it as some function of x times some function of y, and that's what makes it a separable differential equation. One of the observations we can make is that when we divide by the function y, we can write it like this, where we have dy dx equals g of x times h of y. So we can kind of divide out by that h of y term and rewrite it like this. Some function of y dy dx equals to g of x. And then essentially what you could do is, if you want to think of it like this, multiply both sides by dx. And so you'd have some function of y times dy, some function of x times dx, and then we could go ahead and integrate both sides. So the method of solution. One of the things that we have is that whenever we have a one-parameter family of solutions, usually given implicitly, it's going to be obtained by integrating both sides of some function of y dy equals to some function of x dx. That's kind of the goal that we're looking for right now. Let's go ahead and solve this separable differential equation. So we have 1 plus x dy minus y dx equals to 0. It might not look like it's separable right now, but let's do the following thing. Let's get all of the dy terms on one side and all of the dx terms on the other side. So I have 1 plus x dy equals, this cancels, we have y dx. And now what I'm going to do is I'm going to divide both sides by 1 plus xy. Could have done this in 2 steps, but let's just do it all in one. And here's the rationale for that. When we do that, on the left-hand side, the 1 plus x's cancel, and we get dy over y. On the right-hand side, the y cancels, and we have dx over 1 plus x. A function of y on the left-hand side with dy, a function of x on the right-hand side dx. So we can actually now solve this differential equation by integrating both sides. I'm going to choose to write this as 1 over y dy, and we're going to integrate the right-hand side. I'm going to choose to write it as 1 plus x dx. Okay. This one here is an elementary antiderivative. The antiderivative of 1 over y dy is the natural log of the absolute value of y is equal to, here this would be a basic u substitution, that u be 1 plus x, du would be equal to dx, and then we would get the following. This is going to be equal to the antiderivative of 1 over u du, which is the natural log of the absolute value of u plus c. So the right-hand side is going to be the natural log of the absolute value of 1 plus x plus c. So we are able to solve this. Just another thing of note too, by the way, you don't need to put the constant of integration on both sides, because if I had a constant on the left side and a constant on the other side with stuff, you could just simply subtract or bring the constants to one side, and ultimately you're just going to get one constant of integration. So we'll always kind of put that on the side with the x variable, since that's our independent variable. And now we can do a little bit better on this. We can actually solve to get the y by itself. To get rid of the natural log, what we would want to do is raise both sides to the e power. That's going to look like this. E to the natural log of the absolute value of y is going to be equal to e to the natural log of the absolute value of 1 plus x plus c. The e and the ln cancel because they're inverses, so we get the absolute value of y is equal to, here, let's split this apart. We have e to the ln of 1 plus x times e raised to the c power. A common thing that you'll see a lot in our class is this thing here. Remember, e is a constant. We're raising it to another constant. So that in and of itself is just going to be some constant. Okay? And in what's sometimes an abusive notation, we're just going to relabel it as just c. It's not the same c that we see here, but at the end of the day, it's just some constant that we don't really care too much about, unless we need to solve for an initial value problem. So this is just c, or if you feel better, you can call it c twiddle or c something. But then for this part here, again, because e and ln are inverses, This is going to be the absolute value of 1 plus x. We can remove the absolute value bars from the y, because we have a plus minus here. When y is positive, it's positive. When y is negative, it's negative. And then if we wanted to, we can even just kind of absorb that into the constant. So we get c times 1 plus the absolute value of x. And then similarly, that absolute value of 1 plus x, that would be positive when x is greater than negative 1, and negative when x is less than 1. So you could leave it like this, or you could choose to get rid of the absolute value bars and let the constant c absorb the sign there. Okay. So we get our solution. So the solution to this separable differential equation is going to be some constant times 1 plus x. Let's go ahead and do another one. Let's take a look at the following initial value problem. So we're going to be looking at dy dx equals negative x over y, and we want to have the initial condition y of 4 equals negative 3. First things first, we want to bring all the y terms to one side, all the x terms to the other side. So I can take and multiply both sides by y and dx, just declare fractions. So let's clear our fractions. I'm going to multiply by y dx, multiply by y dx. We would get the following. Here the x's cancel. So we get y dy equals, here these cancel, we get negative x dx. We see that it was indeed separable. We have a function of y on the left hand side dy, a function of x on the right hand side. So now we should be able to solve this by going ahead and integrating both sides. We're going to have the integral of y dy. It's going to be equal to the integral of negative x dx. This is going to be equal to classic power rule, add 1 to the power, divide by the new power, equals over here. Again, add 1 to the power, divide by the new power, and lest we not forget, we also have the constant of integration. So we get y squared over 2 equals negative x squared plus 2. Let's kind of rewrite this a little bit more. Let's actually multiply both sides by 2, declare fractions. Here these cancel, so we get y squared equals, the 2's would cancel on this, so I'm going to get negative x squared. And again, that same kind of idea we had a moment ago, if I multiply 2 by a constant, that is still going to be some constant. So we'll just keep that as c. And so we do get an expression for our solutions here. It's y squared equals negative x squared plus c. If you wanted to, you could even get the y by itself by taking a plus or a minus square root. But one of the things that's kind of interesting is if we come over here and rewrite it instead, if I were to add x to both sides, we would get x squared plus y squared is equal to a constant. Some of you might remember from pre-calculus that this is the standard equation of a circle. It would be centered at 0, 0, and would have a radius which would be equal to the square root of c, because you would need a squared term on that side. So one of the things that we might want to talk about is, what would be the domain of definition for our solutions here. Well, especially when you solve it and you get the y by itself, we see that we get the expression negative square root of 25 minus x squared. This would have as its domain x is between negative 5 and positive 5. And depending upon your initial value condition, you would get any one of those solutions.